All right, so we have the problem, consider any function f going from the real numbers to the real numbers. Prove that big F going from the real numbers to R2 defined by f of x is equal to f of x, comma, 2x cubed plus 7 is injective. All right, so the first thing we're going to do is we're going to prove this directly. And we're going to start by let x1, x2 be in R, and let big F of x1 equal big F of x2. So from this means that we get big F of x1 is equal to F of x1, comma, 2x1 cubed plus 7, and F of x2 is equal to F of x2, 2x2 cubed plus 7. Now, from the equality of these order pairs, we then get small f of x1 is equal to small f of x2, and 2x1 cubed plus 7 is equal to 2x2 cubed plus 7. Now, if we can prove that x1 is equal to x2, that means that little f of x is injective, which means that big f of x is injective. So all we have to do is do some algebra here. So we're going to subtract 7 from both sides. We get 2x1 cubed is equal to 2x2 cubed. Divide by 2 from both sides. And we get x1 cubed is equal to x2 cubed. Then cube root both sides. And we find that x1 is equal to x2. So, since for all x1, x2, and r, and if f of x1 is equal to f of x2, we found that x1 is equal to x2. So, therefore, f of x is also injective. If the probability of A minus the probability of A given B is greater than 0, and probability of B is greater than 0, then A cannot be independent of B. So we're going to prove this using contradiction. All right. So we're going to assume the two things that we were given, that the probability of A minus the probability of A given B is greater than 0, and the probability of B is greater than 0. Okay, and then we're going to suppose for contradiction that A is independent of B. Okay, so if A has its independence from B, that means that we have the probability of A intersect B equal to the probability of A times the probability of B. And since we also know that the probability of B is greater than 0, we know that the probability of A given B is equal to the probability of A intersect B over the probability of B. All right. So now we just use these two equations and put them together. So we put this into here. And we get the probability of A given B is equal to the probability of A times the probability of B over the probability of B. Well, we can see that these cancel out. So we're left with the probability of A given B is equal to the probability of A. Now we're going to use our original assumption here and know that the probability of A minus the probability of A given B, well, we know the probability of A given B, so we have the probability of A, and we know that it's also greater than 0. Probability of A minus the probability of A, well, we know that's 0, so we have this inequality 0 is less than 0. We can't have that. That's a contradiction. So therefore, A must be independent of B. All right, easy peasy. We're going to prove by induction that the sum from k equals 10 to n of 2k is equal to n plus 10 times n minus 9 for n greater than or equal to 10. So, for this, we're going to call this equation star, and we start with the base case for induction proofs. So we're going to start, since our problem states that we need to start with n greater than or equal to 10, we're going to start with when n is equal to 10. All right, so the left-hand side of star is going to become the sum from k equals 10 to 10 of 2k, which is equal to 2 times 10, which is equal to 20. And then the right-hand side of star is equal to n plus 10 times n minus 9, but n is equal to 10, so we have 10 plus 10 times 10 minus 9, that's 20 times 1, which is equal to 20. So our base case holds true. Now we have to use our induction hypothesis. So we're going to assume star holds true for n equal to m. Okay? That means that we have the summation from k equals 10 to m of 2k is equal to m plus 10 times m minus 9. All right. And then our third step for the proof is the induction step. So now we must prove that this holds true for n equal to m plus 1. So, in other words, we're going to prove that the sum from k equals 10 to m plus 1 of 2k is equal to, we have m plus 1 plus 10 times m plus 1 minus 9. So we plugged in m plus 1 into the n for each of the n's. We're going to simplify this right side of the equation really fast and get m plus 11 times m minus 8. So this right here is going to be useful in the later in the proof here. So now we're going to work on this sum here from k equals 10 to m plus 1 of 2k. Well, we know using some rules that this is actually the sum of k equals 10 of m of 2k plus, using our induction hypothesis, we know that this right here is equal to plus 2 times m plus 1. Well, we know using the induction hypothesis what this is. It's this right here. So we just plug that in. We get m plus 10 times m minus 9 plus 2m plus 1. Okay, we expand all this out, and we get m squared plus m minus 90 plus 2m plus 1. Combining like terms, we get m squared plus 3m minus 88. And then what we can do, we can see that that vectors out into m plus 11 times m minus 8, which is exactly what we were trying to prove right here. All right, and that completes our induction hypothesis, or our induction step, which completes our induction proof.